personally at 4 civilizations. The Sumerians, the Egyptians, the Greeks, the Mayans, oh, and a 5th one, the Indians. The first one, the Sumerians, were one of the oldest civilizations that we know today. We don't know as much about them as we would like to, because since they're so old, a lot of their writings and a lot of what they had has disappeared. But they had 3 numeral systems: a cardinal system, an ordinal system, and the ternary system. Now technically, the ternary system is considered a cardinal system, but because it's so vastly different, I decided to set it aside separately to look at. The cardinal system had 2 subsystems: a quinary vigesimal system, which is a really long word, and it basically was only for numbers 1 through 60, and it was based on units of 5 and 20. I believe I have, here's the numerals. You can see it goes from 1 to 59 on here. The reason is because when you get to 60, it restarts at the symbol 1, which is confusing, so they decided to only go to 59. The sexagesimal system was for all numbers greater than 60, and it was based on 60. Something that's interesting, kind of confusing about their numeral system is that they only had 2 symbols, a symbol for 1 and a symbol for 10. So as you got past 60, they started reusing things, and so in order to understand what they're talking about, you have to view their math and their use of the symbols in context. Their ordinal system was basically the same as ours today, except for a different language. It's first, second, third, and so on. This kind of concept that was around from even then is where our well-ordering principle comes from. Now, our well-ordering principle just states that every non-empty set of natural numbers has a first or smallest element. If you go through the proof, it basically just states that this is a valid idea, and the idea of 1, 2, 3 should be in order, not 3, 5, 7, whatever. Their ternary system is different because it started out as a verbal system. It was of course a basis of 3, which is why it's called ternary. It eventually became written down, but it only had the 3 symbols, pace, e, and ta. And so once you got into the higher numbers, you started repeating the words, and it got really, really confusing and bulky. And so it became used only for mostly symbolic rituals and having to do with their religion. It was not their main numeral system, as I said. And today, when we look into it, we can see how internally inconsistent it was, which is why it wasn't used as frequently as the main cardinal system. Their mathematics or how they applied their numerals, they had addition, subtraction, multiplication, division. You can see here they had it raised to powers and they did multiplication, and how they set up their symbols is really interesting. You wouldn't normally think of to do that, and it's kind of interesting because you see the square. They make a square out of the symbols for 60. They used geometry and to look at the stars, to study where they were, and to construct things. One of the things that they were known for constructing was the ziggurats. It's kind of in the same as a pyramid, or the same shape. The only difference is it has lots of steps, and so from far off it will look like a staircase. But they also used their numbers to keep a permanent record, because it was very important to them to show people what they saw, and so they created these round circular stones with their observations of the stars and just record keeping in general. The second system I looked at was the Egyptian numeral system. The Egyptian numeral system is very, very highly studied. It was a base 10 system, additive in that, additive meaning you used, like to get to 2, you would use 2 symbols for 1, and so on and so forth. They also had addition, subtraction, multiplication, division. One of the interesting things about their use of their numerals was their multiplication. And they came up with a method of depletion and mediation. Depletion meant doubling and mediation meant halving. So what they would do is, for instance, for 22 times 33, they would have 22 until they got to 1, and they would double 33 until it lined up with the one on the left-hand side. And then on the right-hand side, for every number corresponding to an odd integer, they would mark that and then add those marked numbers together, and that sum would equal the multiplication of the two numbers. And so it's kind of strange that they would come up with that, but it was really ingenious for them to be able to see that. Another thing that they did was they had Egyptians had fractions. They used only unit fractions, basically 1 over whatever number. There were a few exceptions, like 2/3 and 3/4. Now the problem with unit fractions is that if you're only allowing yourself unit fractions, it can become quite difficult to get to the number you're wanting. Another problem was that they were never unique, because, for instance, 7/24 could equal a 6 plus an 8, but it could also equal a quarter plus 1/24. One of the problems with their fractions was that they decided that you could not repeat their unit fractions when you were adding them together. So you couldn't have 1/7 plus 1/7. You had to have a quarter plus 28 or something like that. You couldn't repeat. And so it would get really, really difficult, and they would have to spend a lot of time in order to do this. Some of the applications they had, some of the main ones that we know today, is bookkeeping and construction. Bookkeeping, they decided to keep records of how much they ate, what they bought, who spent what, and just general things like that. We can still find a lot of their bookkeeping records in tombs, which is why we know that it was so important to them. And their construction, of course, is very well known by most people because of the pyramid and such, and their palaces. They were very focused on that. And one of their pyramids, I believe if you took the perimeter of it or something like that, I can't remember exactly, you got 2 pi, or an approximation of 2 pi, which is really, really cool that they had that there. Because even if they didn't have pi exactly, they still were able to see it. They also cited the area of a triangle. However, they cited it wrong. They cited it as a half times the base times the side. The reason they did this isn't because they didn't know that it was a half times base times the height, because of the application for which they were using it. When the Nile would flood Egypt's banks, it would cover the land, and then once the water drained away, they would have to figure out whose land belonged to who. And so what they do is they would base that off of the area of land that they originally possessed. And because the areas of land were so thin and narrow, they were able to do it times the side, which was easier than doing it times the height, and you still got a fairly accurate approximation. They also discovered the area of a circle set equal to 8/9 times d, and then that quantity squared. And from that, they were able to approximate pi. They did that by assuming that if r is the radius, then the diameter would be 2r. Multiplied that, and then by 8/9, and then squared it, and they got 256 over 81 times r. And so they knew that that was always going to be a constant times the radius of any circle, and so that's how they came up with their approximation. Now, something that was also interesting about the Egyptians was their notations for their numerals. They did not change their system or the structure of their system, but they did change how they noted it. It's like when we go from calligraphy to cursive to print, they had hieroglyphics, hieratic, and that was not supposed to happen. Oh, there we go. Hieroglyphics, hieratic, and demotic. Now you can see here in the upper left-hand corner the hieroglyphics and how it's very formal and very it's very well drawn out, and it took them a lot of time to do that. Then they went to the hieratic, and you see it's starting to get more about being fast and less about being ritualistic. And then when you get to the demotic, they completely go away from being set in stone of this is how you do it, and you have to be very careful. They just had general symbols, and they didn't have to worry as much about being neat. The next system I looked at was the Greek numeral system. Now the Greeks had two numeral systems, the acrophonic and the alphabetic. The acrophonic was their first system. It used symbols of 5 and multiples of 10, and what was interesting about them was that that the symbols for them came from the first letter of their numeral words. And so like penta, you use the first letter of that word for 5, and deca for 10, and so on and so forth. Now, it was a mixed system. As I said, it used both 5 and 10, and they intermixed that. Eventually, this system fell out of use, but it was still partially in use because it was used for money in weights. Then the next system was the alphabetic. This system was a base 10 system, and they needed 27 symbols. So they used the 24 letters from their alphabet, and then 3 other symbols, the digamma, kappa, and samphe. You can see right here how they did that. The gamma would be right here, and then the kappa, I think, would be right here, and then samphe would be right there. Now, something that some people don't notice right at first is that they appear to have adopted their structure for their systems from the Egyptian demotic system. Now, the only difference, or the main difference rather, is that they use different symbols, but the structure is largely the same. Now, a lot of people think that the reason for this is because there were Greek merchants that lived in ports in Egypt, and they started to use their symbols in their their selling of things, I guess. But it eventually worked its way into Greek culture, and they started using their structure. Now, you can see the similarities to the demonic in that they were both base 10 systems. They both only used 9 symbols for each exponent, so 1 through 9, 10 through 90, and 100 through 900, and so on. Neither of them had a symbol for 0, though both had the concept. It was mostly, they knew that it was there, but they didn't really delve into that very much. And they both used fractions. Now, the difference from the Egyptians is the Greeks started using unit fractions like the Egyptians, but then they decided that it made more sense to use all sorts of fractions rather than just unit fractions. And so they went a lot farther than the Egyptians in that, and were able to do a lot more in mathematics. A lot of what we know about the Greeks comes from their mathematicians. Pythagoras is one really well-known mathematician, but he's well-known for the Pythagorean theorem. However, he was really a leader of a cult, and he more than likely did not come up with the Pythagorean theorem. It was probably made by one of his followers, but he got the credit because he was the leader of the cult. We get the Pythagorean theorem's name actually from Euclid. He wrote about it in Elements, one of his books, or rather a series of books, because it was 13. He's known as the father of geometry because his books, Elements and Optics, are mostly based in geometry, and we still use that in many of our elementary courses today. Is a lot of the concepts and ideas that he talked about in those books. Optics was a book on the geometry of how the eye sees, which is really cool that he was trying to delve into that idea. Archimedes was another mathematician. He came up with an approximation of pi. Now, he didn't come up with a number, he rather came up with a range of where it would fall. He did this by using infinite sums. He basically took a circle and then circumscribed it and inscribed it with polygons and increased the sides over and over again on both until he came up with an approximation for pi. Another mathematician is Diophantus. He's often called the father of algebra, though there's some debate about that. And he's known for his book Arithmetica. One of his main things that he's known for is the Diophantine equations. We still use a lot of the ideas of his thoughts on algebra, though we've developed a lot more since then. The fourth civilization that I looked at was the Mayans. The Mayans, we know even less about them than the Sumerians in some ways, because their writings were destroyed by Franciscan priests. The reason for that was because the Franciscan priests were terrified of the Mayans reverting back to their pagan ways and starting human sacrifices again, because to them that was absolutely horrific. So most of what we know about them comes from inscriptions on their monuments that they made to their kings and probably their head priests, and also from personal collections, because before the Franciscan priests destroyed everything, some of the writings and artifacts from the Mayan civilization was sent back to Europe and was kept in personal collections, and so we still have those today. Now the Mayans only had 3 numerals: a dot for 1, a bar for 5, and an empty shell for 0. They used a bigesimal system for any number greater than 19, so they kind of switched as they went along. But here you can see here their system going through 14, how they stack their numerals. And then you get to the bigesimal notation, and they start using more of an idea of bases, where you have 2 and 3 here, but instead of being 2 and 3, it's 2 times 20 plus 3. And then you go through and the same idea applies. Another interesting fact about Mayans is that they used 0, which is different from other civilizations. They used it as a placeholder and number, and they viewed 0 also as their death god, which is interesting because 0 is nothingness, so they viewed death probably as nothingness. And they became so obsessed with this idea that they decided to create calendars to prevent nothingness from happening. They had the Hab, the Sulcan, and the long count. The idea was that if one of them failed, the other one would act as a backup, and that would prevent time from stopping, which was terrifying to them. Now, the Hab was a 365-day calendar. It had 18 months with 20 days on each month. Now, the interesting thing about that was that each month began with day 0. Now, on day 0, since it was a type of transfer day, because the thought was that the god of that month laid down his burden, and the god of the next month would pick it up and carry on. But on that day, they would do nothing. Everything would just stop, because it was just considered that was what you did on day 0. At the end of each year, they added 5 days. It seemed to be some sort of insurance to make sure it continued to go on. Now, the Sulcan calendar was a 260-day calendar, and it was interesting because it had 2 cycles: 13 numbered days paired up with 20 name days. So you go through 13 numbered days paired up with the first 13 names, and then when you get to the end of the 13th cycle starts or ends, and you get to the next one, and that number 1 would pair up with the 14th name day, and it goes on and on. And now when the calendar lined up with the Hab, they would celebrate that with human sacrifices to give the gods strength so that they would continue to go on, and so that the death god 0 would not win. The last calendar was less of a calendar and more of a countdown, you could say. It was a count from the beginning of time. They set a time when they thought time began, and then they could tell when they were based on how much further they had gotten from that date. They had different applications for this, though they seem to be mostly surrounding their idea of their gods and their idea of time. As I said, they used their numeral system to keep track of when they were. They studied the stars to make their calendars. They built temples, palaces, and cities, celebrating their culture and their nation. They invented calendars, as we've seen, and they made rituals based around these calendars to appease their gods. And all in all, it just came down to the fact that they became obsessed with time. They became obsessed with controlling time, which is how they saw it, as something to be controlled. They made brilliant calculations because of this fear, and very complex calendars because of it as well. And so it's fascinating to see what fear will do to people if it's strong enough. The last civilization I looked at was the Indian numeral system. Now their numeral system, our numeral system is largely based on theirs. We have the same decimal system, 0 to 9. And you can see the evolution of their numeral system from their original numeral system to ours today. And you can see as you go through that some of the symbols start out as one thing, and then by the end they become something else. But the idea is still the same. They didn't start out with 0, but as you see, as they went along, they developed that idea. Now their system is different from others because they viewed their numerals and their math as something that needed to be separate. So they, instead of using objects or other things to represent their numerals, they made completely new symbols so that they were abstract. Another interesting thing about theirs was that they were a positional system. So 506 couldn't equal 650 or anything else. If it said 506, it meant 506. For them, 0 wasn't just a placeholder, it was a functional number, fully functional number. Because of this idea, they were able to come up with positive and negative numbers and not only develop them, but use them. We have many mathematicians from that era that we can look at. I'll look at 4. I'm not sure if I pronounced these right, but I'll try. Aryabhata was one of them. He wrote one of the oldest math textbooks and solved many things. One of them was Vy equals Ax plus C. He came up with a formula for sums and progressions. He delved into square and cube roots and solving those. And he even accurately computed pi out to 4 decimal points. Now the interesting thing about that is other civilizations came up with really accurate approximations, but he actually computed it out to 4 decimal points, which for the time and for the information that he had is really impressive. Another mathematician was Brahmagupta. The main thing I could find out about him was that he developed a formula for an area of a cyclic quadrilateral, which is a really long name. His formula was that A equaled the square root of S minus A times S minus B, S minus C times S minus D, where A, B, C, and D were the sides of the quadrilateral, and then S, he said, was half times the sum of all the sides. And so, the interesting thing about all these mathematicians is that they actually didn't come up with proofs for what they had. They just said that they were true, which we can look back now and say, okay, based on what they did, we can make proofs of their math, but they didn't have them originally. Another mathematician was Sridhara. He's known for developing the quadratic formula. He looked at the equation x squared plus ax squared plus bx plus c equals 0, and said, well, if we multiply that by 4a, then we can carry it out until we solve for x, and then we get x equals negative b plus or minus the square root of b squared minus 4ac over 2a. And so, even though he didn't have proof for this, he was correct in his thinking that this was how you solve for x, which is really interesting that they were able to do that. Another one, the last one that we'll look at is Bhaskara. He discovered irrational numbers. Now the Greeks also discovered irrational numbers, but the interesting thing about him is that instead of treating them as with fear, he decided that they needed to be controlled. They needed to have rules so that they could be used. And so he created rules so that he could add them together and do various things with them. In our society today, we use this knowledge. We use a decimal system from the Indians, and we intermix it with elements from other societies, such as the sexagesimal system from the Sumerians, and a duodecimal system, which came more, I think, from the Anglo society. But we built upon these other civilization systems of the knowledge that they have, and the math they developed from their systems, and we use that math and the math that we've discovered for ourselves in every aspect of our lives. Our foundation, one of the foundations of our society is built upon this knowledge of math. One of the discoveries that we've made in our society today was the fast Fourier transform, which is basically a quicker way of doing a discrete Fourier transform, which is used for spectral analysis, filter banks, and there's a whole bunch more that it's used for that I can't remember all the things. But it's very important to our society, and there's so many things in our society that we've discovered that we use every day without even realizing it. So, in conclusion, I went through this, and I can see that you can see their beliefs, what they held true in their numeral systems, and how they use that in mathematics. And if that's true, then the question remains, how will future generations see us and see our use of math, our use of our numeral systems? I can't answer the question because it's something in the future, but it's a really interesting question to think about.
All right.